Is Tomoyuki Amano from the University of Electronics and Communications from Japan. First of all, I appreciate Prof. Christopher for organizing this nice symposium. Merci beaucoup. This is first I met Prof. Christophe in 2008 in Brussels. Uh, and sorry. This is Prof. Christophe and Prof. Hari and Prof. Taniguchi. And this is talk of Prof. Christoph. Very nice talk. And this is Prof. Hari and Prof. Taniguchi. And this is me and Prof. Christoph. And we I made in the time I made a friend with Prof. Christoph, very young. And 2009 in Brussels, this is second time I met Prof. Christoph. And that is Prof. Christoph, Prof. Harry, and that man is Dominici, who comes to last night. And next, this is a picture of Prof. Hari and Prof. Taniguchi, and this is poster of Brussels-Waseda seminar. So Brussels and Waseda has a good relationship. Then I start my talk. Today I talk about nonlinear time series model. And we use instrument barrier method for nonlinear time series model. First, I give introduction. In nonlinear time series model, the conditional least scarce estimator, for short, I call this estimator as serial, is one of the fundamental estimator. But if explanatory variable, that is past variables, disturbance are correlated, it can't be consistent. To treat this problem, we apply the instrument variable to serial. Next, we give the short history of instrument variable method. The instrument variable method was developed in a linear time series model. In linear time series model, it is assumed that externality variables and disturbance are independent generally. But many times, there are occasions that this condition is broken and the ordinary least scarce estimator is biased. And so to overcome this difficulty, Wright and his son Wright proposed instrument variable method. And the other authors developed this method. Please, comprehensive reviews are seen in white. Recently, Amano, Kano, Kato, Taniguchi applied this method to CAPEP model. In this talk, we first introduce nonlinear AR model, and then we apply CL to this model, where we assume explanatory variables and disturbance are independent. And we derive a condition that CR is asymptotically optimal. Next, we apply CL to nonlinear AR model, where we assume explanatory variables and disturbance are correlated. And we show it can't be consistent. So we use instrument variable. So first we give the example of instrument variable, and then we apply the instrument variable method to share, and we estimate the parameter of nonlinear AR model, and we show that this new estimator is consistent. Next, we define nonlinear AR model. Nonlinear AR model is a very large model. And that this model includes SET-AR model and XP-AR model. This is the definition. Nonlinear AR model given by like this. This. Where xt is a random vector, and f theta is a vector valued measure function, and ut is a disturbance vector, and we assume ut the mean of ut is 0, and the covariance matrix is identity matrix. This is identity matrix. And this has, we assume this has density F. And we are interested in this parameter theta. This parameter theta, we are interested in this parameter theta. Next, for this model, we define CL for CL. CL defined by minimizing this finity function. This is a conditional expectation. And this FTM is a sigma algebra generated by this set. Then CLS meta is obtained by minimizing this equation. First, we assume we investigate this CLS meta under this condition. And that is ut and past values xt are independent. From Joestem, CL has asymptotic normality, where this is asymptotic variance. Next, we evaluate the condition that this CL estimator is optimal based on RAM. For this, we prepare Kato, Taniguchi, and Honda's result. Under regularity condition, nonlinear AR model has line, and its feature information gamma is given by like this. And this large F is given by like this. And from this lemma, asymptotic variance is larger than that is larger than gamma inverse, and if this equality holds or CL is asymptotically optimal. And for this equality condition, we give the condition. And that is necessary and sufficient condition that this equality holds is disturbance follows Gaussian. From under this condition, CL is asymptotically optimal. Note that under this simple condition, CL is asymptotically optimal. Next, we evaluate CL under this condition. That is, UT and past value XT are correlate. From just them, CL is a condition if this assumption holds. That is partial derivative of finite function over n convert to 0. And if we calculate this term, is this. And this doesn't convert to 0 because past value and disturbance are correlate. Hence, CL doesn't satisfy the condition of consistency. So we use instrument variable method. First, we give a simple sample. This is example. YT follows linear model, where xt is a random vector and beta 0 is parameter and epsilon t is disturbance. And this model has this representation, where this vector y is past value of yt and large F is given by like this, and epsilon is disturbance. And from this representation, ordinary case estimator, first short, we write OS and use this notation as this representation. From this representation, if conjugate expectation is 0, so OS conjugate expectation of OS is beta 0. So this OS is consistent. But if conjugate expectation is not 0, so conjugate expectation of OS is not 0. So we consider the instrument variable. We assume that T follows k dimensional. And we assume that T is uncorrelated with disturbance. By use of this instrument variable, this equation hold. So from this equation, the parameter beta 0 is estimated by this, where this large F is given by like this, and so the instrument barrier estimator is given by like this, Here, sorry, and this instrument variable estimator has this representation. So we assume ZT and epsilon T are independent. So this estimator, this instrument variable estimator is consistent. Next, we apply this instrument variable method to our nonlinear AI model. Please recall that nonlinear AI model for this. And we assume f theta is a vector value measurable function. Now we impose this condition again. That is disturbance ut and past values xt are correlated. In this setting, CL, CL is not consistent. So by use of the matrix type instrument variable, we introduce this penalty function or Q tilde. That is this x is past value of x and f tilde is past value of f theta and z is past value of zt. So by use of this new penalty function, we propose an instrument variable CL estimator. For short, we call ICL and we use this notation. And this ICL is given by minimizing this penalty function. And we calculate this penalty function or Q tilde. So this term given by like this. And hence we have this term converged to this. And ut and zt are independent, so this term 0. So this ICL satisfy a crucial condition or crucial stem. So from this result, that is this our ICL estimator converts has asymptotic normality and asymptotic variance is given by like this. Finally, we give concluding remark. That is we investigate this nonlinear AI model, and under this condition, UT and XT are independent. CL is asymptotically optimal if and only if UT is Gaussian. But UT and XT are correlated. CL doesn't satisfy the condition of Jostem. And but ICL, our ICL, new estimate ICL is asymptotically normal. Thank you very much. That's all.